Right.
So far, so good?
All right. We left off with question 22 on this AP Calc exam here, Calc AB exam. Let's just review the chain rule.
Okay.
If I have a function y equals u squared, and I want to find dy dx, well, I can't find dy dx directly. I can find dy du, which is just 2u, but then I have to multiply it by du dx. And notice how the fractions work here. That cancels with that, and I end up with dy dx. So if you're ever having to remember this, notice that this is the derivative of the outside. That is the derivative of the inside. So if I had y equal sine of 3x, and I want to, this is actually a composite function, I would let u equal 3x. So now I have y equals the sine of u. Well, that's like that. Y is a function of u now. So if I wanted to differentiate this, I'd have to differentiate and find dy du. Well, dy du is cosine of u. But what is du dx? That's 3. So it would be dy du times du dx. So it's the derivative of the outside times the derivative of the inside. So it'd be 3 cosine of 3x, since u is 3x. Okay? So that's the way the chain rule works. Refresh me. You didn't think you'd had the chain rule. Is that correct?
No, I have had the chain rule.
You have had the chain. You've had the power, the product, the chain, and the quotient?
Yes.
Okay, cool. I didn't really need to explain all of this. Although sometimes it helps. In other words, if you have a function where you're not quite sure what u is, it helps to understand that.
Mm-hmm.
What's the inside here? What would u be?
Sine?
Uh-huh. Yeah, because we know how to integrate y equals u squared. The derivative of the outside is just 2u. The derivative of the inside is cosine x. So I end up with 2 times sine x cosine x. Now, if I change it just slightly, now what's u?
X.
X squared.
Right, x squared.
Because we don't know how to take the sine of u squared. That would be a difficult one to take. But we do know how to take the sine of u. So if I let u equal x squared, well, now I've got the sine of u. So y prime is going to be the cosine of u times du dx, which is 2x, which is the cosine of x squared times 2x. So if ever you have trouble figuring out what the inside is, just use that analysis. Notice that if I did let x equal u, well, now I've got something that's just as difficult to differentiate. I don't know how to differentiate that. I can't use the power rule because it's the argument of the sine that's being squared. That's not sine u times sine u. That's the sine of whatever u is squared. All right, so let's look at 23. Let me blow it up just a little. Once again, I apologize for the blurriness of it. So if we'll write it like this. I don't need to really write it like this, but just for clarification, I will. What's the first rule we're going to have to use to get y prime here?
Product rule?
Yeah, we got the product of that function times that function. And they are completely different functions. They cannot be combined. So I definitely have a u and a v. Now, the one thing that is important is if I let that be u and let that be v, both u and v have to be functions of x for me to use the product rule.
Right.
Okay. So let's do it the way we talked about last time, where we always start with that and then take the derivative of that and then do the reverse. Okay. So I'll get you started. That's u. What's v prime? Do you know how to take the derivative of a to the x? If
X to the a, like x times a to the x minus 1?
Well, here's the way I remember it. No, you can't use the power rule. If it was e to the x, what's the derivative of that?
E to the x?
Yeah. But if it's 2 to the x, then the derivative is very similar. It's natural log of 2 times 2 to the x. So it's a lot like e to the x. You could say that if y equals e to the x, the derivative would be natural log of e times e to the x. Well, the natural log of e is 1, so you lose the 1. But when you have a base other than e, it's the same thing, only multiplied by the natural log of the base.
Oh.
Okay, so what is the derivative of 5 to the 2x?
Ten to the 2x?
Now, start with natural log of 5
Right.
times 5 to the 2x. But because that's 2x, you got to apply the chain rule. What's the derivative of the inside? 2.
Okay.
The inside being 2x. In other words, if you force me to use U substitution, I'm going to let u equal 2x because I know how to take the derivative of 5 to the u. That's what it comes down to, is that if you ever are in question as to what to make the inside, go to U substitution and then see if you can differentiate it with U substitution. Now, that is all we did was u v prime. We have to add to that the reverse, which is u prime v, right?
Right.
I mean, using the product rule. So far, we only have this much of it. So what's the second part? So it's plus, and now we're going to take the derivative of that times that.
Right.
It's the derivative of natural log. It's 1 over.
1 over?
Yeah, the derivative of natural log of x is 1 over x.
Right.
That's an important one to remember. That you'll use that tremendously
So,
in differential and integral calculus.
so it would be 3 over 3x,
Yeah, very good.
which makes it
1 over x,
1 over x.
which is interesting, isn't it? That means the derivative of the natural log of x is the same as the derivative of the natural log of 3x. Times 5 to the 2x. We don't do anything to this. In other words, we're not taking the derivative of that. That's just v. We did u prime times v. Now, if we look at all of those answers that we're looking at there, well, let's see. This part here is that, or this, or this. A, B, or E. We know it's being added. So is this what we wrote up here? Well, there's my 2. There's my natural log of 5. There's my natural log of 3x. And there's the 5 to the 2x. So it looks like A is that right there.
Right.
And notice that cannot be simplified. In other words, natural log of 5, well, it could be, I guess, if you want to look in your calculator and come up with a number. But if you want to list these things exactly, then natural log of 5 times natural log of 3x is as simplified as it gets. There's no log rules where you can combine those things. If they were being added, if it was the natural log of 5 plus the natural log of 3x, then that's the same as the natural log of 5 times 3x. But when the log functions are being multiplied, there's no simplification.
Right.
All right. This, one of these has a misprint. I don't think it's this one, though. Here, I think it might be, no. What is that? That must be 1 over t. Hold on a second. Yeah. Okay. So, we have the subtraction of two functions. That's the derivative of the subtraction of each. In other words, u prime t is the derivative of this minus the derivative of this. So, what is the derivative of e to the 3t squared?
Would it be 3 times, well, right, is there multiple chain rules in this?
No? In other words, if you had to let u equal something, what would it be?
Three t squared?
Yeah. Because I can differentiate e to the u. E to the u is just e to the u, but here I'm going to have to multiply it by the derivative of the inside. So my answer is going to be e to the u times the derivative of that, which is 6t. So that's the derivative of that part.
Right.
Now, what is the derivative? And let me write this a little different way.
Okay.
Instead of e to the, I can't even be certain of what it is. I can't read it. It's e to the minus 1 over t. Or, let's write that as minus t to the minus 1. Only because it'll make it easier to take the derivative of it if I use a fractional exponent rather than having to use the quotient rule or anything. So what would u here be?
Negative t to the negative 1.
So what's the derivative of the outside?
T?
It's the derivative of that out.
T to the negative 2?
Same thing. You're not applying the chain rule. In other words, I'm going to let u equal that. So what I really have is e to the u. So what's the derivative of e to the u? E to the u. Times the derivative of the inside. Well, there's my e to the u. And now what's the derivative of that? In other words, my du dt is what I have to multiply this by. So all I did was take the derivative of the outside. Now I've got to take the derivative of the inside. Now you can use the power rule. So what's du dt? Working just with this on the right side.
T to the negative 2.
You got it. So I have to multiply this thing by t to the, it's negative. It's positive, which makes it positive, right? In other words, it doesn't turn that into a positive. But du dt is positive. This ends up being t to the minus 2.
Right.
So this is my answer. Now let's see if I can find it on there. Well, here's the 6t. There's only a couple of them that have a 6, b and d. So it's one of those. And then looking for a minus, well, there's the e to the minus 1 over t right there. And there's the t to the minus 2 right there. So the answer is D. And if you want to write it back with positive exponents, you'd write it exactly like that. In other words, they frequently don't like negative exponents. They want all your answers to have positive exponents. So this would become e to the minus 1 over t divided by t squared, instead of multiplied by t to the minus 2.
Right.
And now I don't have any negative exponents, and everything is as simplified as I can get it, pretty much. I mean, I could do a lot of fancy algebra to try to combine that, but obviously they don't do it here. You know what I mean by the fancy algebra? In other words, I could find a common denominator to combine these two fractions, things like that.
Yeah.
Which sometimes you have to do, sometimes you don't. I mean, how far you simplify it is frequently kind of based on the nature of the problem. A lot of times, if I was going to take a second derivative of that, then I probably wouldn't want to be looking at it like this. But maybe. Notice that sometimes, let's just look at this again. What I have circled here is the same thing as what I have down here. But let's say the second part of the question was find the second derivative of it. Well, it's easier to leave it like that to find the second derivative of it. I only have to use product rule. If I'm dealing with this, I got to use quotient rule. Well, we both know the quotient rule is more complicated and difficult to deal with than the product rule. And you can almost use the product rule exclusively. In other words, you can pretty much turn any quotient into the product rule, right? If I wanted to take the derivative of this, well, why don't we write it like this? And now use the product rule. You can do that, always. In fact, for a long time I did, when I didn't have the quotient rule memorized. I just turned everything into the product rule, which I had memorized. But there are some situations where you have to know the quotient rule. And it'll be the easier way to do it also. Now, have you done derivatives of trig functions? You have, right? We went over those?
Yes.
Okay. And how about the derivative of inverse trig functions?
Not really covered that much.
Well, let's go over them. There's three main ones you need to memorize. One is the inverse cosine. You know what? The easiest one is tangent. Arctan of x, if that's y, then y prime is 1 over 1 plus x squared. Fairly straightforward. If it's the arctan of u, and they want dy dx, then I got to multiply this whole thing by du dx also. You get that, right? In other words, the problem with this notation, y prime, is it doesn't really say the same thing as dy dx. Dy dx is much more robust because it tells you what are you differentiating. You're differentiating dy dx. The dx is a big part of it. If I just write y prime, that doesn't tell me what I'm differentiating it with regards to. Let's say that my function was arctan of u, and I wanted dy dx. Well, I got to take dy du, which is this, times du dx. And that will give me dy dx. But that's the same thing as the chain rule. Derivative of the outside times the derivative of the inside.
Right.
So, if we know that the derivative of the arctan of x is 1 over 1 plus x squared, and incidentally, when you take derivatives of the inverse trig functions, you always get polynomials. You do not get trig functions. Which is interesting, because when you take the derivative of trig functions, you always get trig functions as answers. But when you take the derivatives of inverse trig functions, you always get polynomials as answers. So this is arctan. Let me do the other main two, which are arcsine and arcsecant. Arcsine of x, so we don't have any chain rule, then y prime is equal to 1 over the square root of 1 minus x squared. And the third one, and you only have to memorize these three because the others are just the negative of these. Just like when you take the derivative of the cofunction, it's always the cofunction with a negative sign on it. Well, when I take the derivative of these, hold on, it's arc secant, that's the third one. Then y prime is 1 over x times the square root of x squared minus 1, actually the absolute value of x. So those are the three you have to memorize. Notice their similarities. Notice the easiest one is arctan. There's no radical sign involved. The next easiest one is arcsine. It's just the square root of 1 over the radical of 1 minus x squared. And notice arcsecant is the radical of x squared minus 1. But in front of that radical is the absolute value of x. So maybe one way to memorize this is arcsecant has the x's next to one another. Arcsine is the reverse inside the radical. Instead of x squared minus 1, it's 1 minus x squared. And tangent addition is going on in the denominator, and there's no radical sign. Now, when I said these were the only three you have to memorize, the derivative of arc cotangent is this with a negative sign. The derivative, and that's because cotangent is the cofunction of tangent. Not because it's the reciprocal, but because it's the cofunction. Well, what's the cofunction of sine?
Cosine?
Cosine. Cofunctions are the trig function with the word co in front of it. That's what makes a cofunction. As it can be a little confusing, especially with the way I teach reciprocals, because I teach reciprocals that there is one co in every pair, but these are not cofunctions. These are reciprocal functions. Turns out that that's both reciprocal and co. But these two are not. But notice the rule I gave you to remember these were every pair of these has one co. There's the co right there.
Right.
There's the co there. There's the co there. As long as you remember that, you won't get them ever mixed up. But cofunctions are completely different. Cofunctions actually have different properties. And the property is the sine of x equals the cofunction of 90 degrees minus x, or pi over 2 minus x. This is the relationship of all cofunctions. And in fact, cofunction of x equals the sine of pi over 2 minus x. Notice that the sine of 30 degrees is 1/2, and the cosine of 60 degrees is 1/2. So if I put 30 degrees in here, that means the sine of 30 equals the cosine of 60. And it does. So cofunctions are defined like this. This is the relationship between cofunctions. And if I put the others down there, secant of x equals cosecant, its cofunction of 90 degrees minus x, and tangent of x equals cotangent of 90 degrees minus x. So those are the properties of the cofunctions. But the cofunctions are the ones you want to remember when you're doing derivatives. Notice that the derivative of sine is cosine. The derivative of cosine is whatever the cofunction of that is, well, that's sine, but with a negative sign. Derivative of tangent is secant squared. The derivative of cotangent, we know, is going to be the negative, whatever the cofunction of that is, which is cosecant squared. And finally, secant, the derivative is secant tangent, and cosecant negative cosecant cotangent. So you really only have to memorize those three to know all six. All right, back to inverse. The inverses are a little similar because, like I said, if you memorize that, then you know the derivative of the arc cotan is just the negative of this. Put a negative sign in it, and you got the derivative of the arc cotan. Same thing with the arc sine. If I want the derivative of the arc cosine, put a negative there. Derivative of the arc cosecant, put a negative there. So you only have to remember these three.
Okay.
Let's look at that one right there. What would this be?
Arctangent?
Uh-huh. Arctan of x plus c. In other words, if this is the derivative of arctan, then the integral of that has to be arctan. Because the derivative of this must equal that.
Right.
So, this little problem they gave us here is the integral of e to the 3x divided by e to the 6x plus 1. If I let u equal 3x, what is this integral in terms of u?
U over u squared plus 1.
I didn't let u equal the right thing. I need u to equal e to the 3x. Because now it would be u over u squared plus 1. Hold on, I'm thinking for a second. Problem is we don't know the integral of that. That's not 1 over u squared plus 1. If that was 1 over u squared plus 1, we'd be in clover. What if I had, okay, let's see what they have to say. Sometimes they can do a better job of explaining it than I can. If they first rewrite this integral using U substitution, u would be e to the 3x, and du would be 3e to the 3x. Well, what they really mean to say there is du dx would be that. Incidentally, for your information, you cannot have a partial derivative like this. If you have a du, you better have some other d, dx, dy, something else. So what they meant was du dx equals this. All right. So we're going to have to use the chain rule here also. First of all, let's go with this. You know that whenever we're going to use U substitution to solve an integral, we're going to need to find the derivative of that. So, questions?
No.
Okay. And I want to really solve for dx. So I treat them like fractions. And now dx becomes du over 3e to the 3x. So if I'm substituting, I've got in this case u, that's my e to the 3x right there, over u squared plus 1, but u is just e to the 3x, right? And what is dx? Dx is this. And I can write it like that. du over 3e to the 3x. And now, through the miracle of substitution, the derivative, the x's go away. That cancels with that, and I'm left with an integral that's completely in u, which is what I want. I can only integrate if it's completely in u. I still have a 3 down here. I'm going to take that 3 out of the integral like that. Just see how I got to this step.
Yes.
Okay. What's the integral of this?
Arctangent?
Arctangent. So my answer is 1/3 arctan of u, but u is e to the 3x, so I'll resubstitute, plus c. And that answer is E.
Right.
That's a pretty hard one. I would suspect, well, it's not that hard. In fact, the moment you hit integrals with U substitution, you did that last year, right?
Right.
Okay. Let's go over that just so you understand it just a little bit more. I'll give you a couple of examples. Yeah, let me use this. Here we have the product of two different functions. right?
Right.
Can't integrate products very easily. So the first thing you look for when you're trying to integrate a product is to see if one of the two entities is the derivative of the inside of the other. And it is. What's the derivative of that? 2x. What's sitting right next to it? 2x. That means if I use U substitution, I can turn this entire thing into an integral in U, and I won't have any x's left. So how would I do it? What would I let U equal to? Work me through this whole process, starting with this over here on the right. Is U going to be x squared plus 1, or is U going to be the square root of x squared plus
1? X squared plus 1?
Remember, another way of writing that is like this. Now what's U going to be?
X squared plus 1?
Right, because I can integrate U to the 1/2, right? I can use the power rule.
Right.
Okay, so that's what I'm going to let U be. It's x squared plus 1. Next step. Remember, my goal is I'm going to substitute for every single thing that's in there and turn this integral in x into an integral in U. So I got to substitute for that also.
Well, du would be 2x.
Du dx is 2x. Don't forget the dx part. That's very important. They actually left it out in their answer, and it was incorrect to leave it out. Now you treat these like fractions. So what's du equal to? In other words, if du dx is equal to 2x, what's du equal to?
Dx over 2x?
Well, you multiply both sides by dx, right?
Right. All right. Sorry. I was thinking too far ahead.
It's okay. So that's what we get. Now, we could do it the way we've been doing these and solve this for dx, which puts the 2x in the denominator. Going to cancel out with that. But there's actually a little bit of a shortcut that you can save a couple of steps here. Do you find that anywhere in our problem?
I see dx.
Yeah, the 2x is way over here and the dx is way over there, but they're all still being multiplied together. So, in other words, I don't have to actually solve for dx and substitute. I can substitute for what I see. I see a 2x there and a dx there. So immediately I can substitute du and take out that and that. And I've saved myself 2 steps actually, because now the problem immediately turns into u to the 1/2 du. Very simple to integrate. What's the integral of this? The way I do my power rule, I think it's a little different than the way you do yours. You can do it either way, whichever works for you. But for me, the thing that works the easiest is to immediately add 1 to the exponent and divide by the new exponent. Those are the only 2 things you need for the power rule.
So
add 1 to the exponent.
U of 3/2?
Yep. So that's the integral of that, plus c. And now, of course, that answer isn't going to be on there because all of their answers are in functions of x. So we have to go back and resubstitute for u. So it's really 2/3 times x squared plus 1 to the 3/2 plus c. And that answer Oh, this is a problem I made up. Yeah, we're not doing a problem on this test. I made this up just to illustrate U substitution. And what we look for when we're going to do U substitution. We look for a very critical thing. When we're looking at this problem, let's erase everything else here. We first have to figure out what we would make U, and what would the derivative of U be. And we know that the derivative of U always ends up in the denominator when we do it the old way and substitute for dx. And so we need the derivative of the inside to be 2x. Well,
Right.
what if it was only that? Could I still do it? Yes.
No.
Well, here's what I would do. This that I've written right here is the same as if I put a 2 there, excuse me, a 1/2 there, and a 2 there. Same thing. I haven't changed anything. Right? Because I can always bring constants outside the integral sign.
Right.
So 1/2 times the integral of 2x times this quantity is the same as the integral of x times that quantity. In other words, we don't need that to be precisely the derivative of that, because all we need it to be is the same power. It doesn't need the proper coefficient. We can always get the proper coefficient in there.
Right.
If I had this problem, can't use substitution. Notice why. The derivative of the inside is 3x squared. That's never going to get rid of this x. If I try to use U substitution to integrate this thing, I'm going to have an x in the bottom that I won't know what to do with. In other words, the only way U substitution works is if you can actually get rid of all of the x's before you turn it into an integral of U. So this one here, I would not be able to use U substitution. Furthermore, that's a pretty difficult integral. I'm not sure what I would use to integrate that. That's one of those integrals that, in other words, you've already learned maybe you've learned two techniques now that I remember. You've learned the power rule and you've learned U substitution, and that's it, correct? I don't think you've learned integration by parts. I don't think you've learned integration by partial fractions. I don't think you've learned integration by trig substitution.
No.
And yet, those 5 methods of integration might only handle 20% of the functions you'll come across in real life. In other words, we're going to use this in real life, so you're going to have integrals of actual functions, and very few of those actual functions are going to fit our rules very nicely. That's why integration is so much more difficult than differentiation. You can make the function as complicated as you want, and between the 4 rules of differentiation, I can differentiate it. It may take me, 117 lines on the paper to do it, but I can do it. Whereas integration, all I got to do is make this thing slightly more complicated, and I don't know how to integrate this. So it's a whole new story. But the fact is it doesn't matter, even if that was 3x squared in there, now I can use U substitution. Because the derivative of the inside is going to be 6x. Well, I can make this 6x by putting a 6 there and a 1/6 out there. Now I'm all set to go, using basically the power rule. And in fact, a lot of classes won't even call this U substitution. They will say, just use the power rule on this part, because the derivative of the inside is sitting next to it and is going to disappear. So I could integrate this rather quickly without U substitution by just saying, well, it's going to be 3x squared plus 1 to the 3 halves, whole thing times 2/3, and there's my integral. That quickly. I don't need to do the U over here because I can tell that I'm using the power rule. Basically, what I have is f of gx times, in other words, whenever, this is the way they'll write it in the book. This is what you're looking for, is a composite function. That's what that is a composite function, times the derivative of the inside. And whenever you see that, you can use the power rule on that alone to answer it. So that I can't integrate. I don't know how. Well, actually, I do know how, but that's towards the end of. In fact, you don't get this in Calc BC. You get this in Calc 3, the next calc beyond that. But I don't know how to integrate this. Notice I can't just use the power rule. Power rule would give me sine 7th of x divided by 7. But notice that if I take the derivative of that, I don't get that. Because when I take the derivative of this, I'm going to have to use the chain rule and multiply it by the derivative of the inside, which is sine x. So the only way I'm going to be able to easily integrate that is if I've got a cosine x next to it, like that. Now I'm looking at f of g of x times g prime of x. That's what I'm looking at now. This is a composite function because it's basically a combination of sine x and x to the 6th. That's what makes it a composite function. So that's the most important thing to look for when you're doing these integrals where you would normally use U substitution. Now, there is another kind of U substitution that's significantly different than this. We got about 8 minutes, it'll work. I just have to figure out how to, let's see. Notice I can't integrate that. Or can I? Hold on. Yes, I can integrate that. What am I thinking of here? Hold on. Because that would just be the integral of x plus 1 to the negative 1. The derivative of the inside is 1, so I don't have to worry about it. So I can just use the straight power rule on this. This is what I meant to write. Can't use the power rule on this. The top is not the derivative of the bottom. I can't use typical U substitution. There's really only two kinds of U substitution that I know about, and that's one where the top is the derivative of the U, but this one's a little different. Watch what happens when I use U equal x plus 1. What's du dx?
1.
Which means du is equal to dx. Now let's go ahead and substitute everything up here. Well, if u equals x plus 1, then x equals u minus 1. Right? That's the numerator. The denominator is u, and dx is du. So by just using this substitution, I've turned it into an integral in u. Now you might say, well, this doesn't look any easier to integrate than this, but it actually is a lot easier to integrate. Why? Because I can break this up into two fractions. I can't that. I can't break that up into x over x plus x over 1. If I could, I'd do it, and I could integrate it really easily. But as long as I have a single variable in my denominator, I can break it up into two things. So this actually becomes the integral of u over u minus the integral of 1 over u, both of which are very easily integratable. What's the integral of 1?
X.
Well, what's the integral of 1 du? It's not x, it's u. In other words, it's whatever that variable is. So this would be u minus, what's the integral of 1 over u? Natural log of u.
Right.
And this comes up over and over and over in calculus. And that's why I say this thing that you need to memorize, that the derivative of 1 over u is the natural log of u. Because most of the time you're going the other way around. You're trying to find the integral of 1 over u, which is the natural log of u. So now we have our answer. Because u is x plus 1 minus the natural log of x plus 1. And plus c. So I'm able to integrate this thing here only by U substitution. No other way. And yet it's not traditional U substitution. This is actually a U substitution where you can end up defining x in terms of u, which is what we did to write that. In other words, if I want to turn the entire integral into an integral of u, I can do it, and I will do it as long as I can integrate that integral. Here's an integral I didn't know how to do, but I know how to do this one. They look similar, but they're not at all. This one has a single denominator. This one had a denominator with 1 being added to it. And that made all the difference in the world in terms of being able to integrate it. So these are the two different kinds of U substitution. One is the f of g of x times g prime of x, and the other is called change of variable. This is change of variable, where I've defined u in terms of x, but then I also define x in terms of u. In other words, this also means that x equals u minus 1. And so I'm going to substitute that for x when I get to it. And this is kind of the classic problem, this problem right there, only because it works so nicely on this. I really do not have a way of integrating this without U substitution. If it was just 1, then the answer is natural log of x plus 1. But having that x in there changes everything. Now I have to use U substitution in order to change it into an integral that I can actually integrate. And this is another concept in integration that's fairly critical, is that the integral of the sum is equal to the sum of the integral. Or I should say the integral of the sum or difference is equal to the integrals, or the sum and difference of the integrals. In other words, going from this step to this step is what allows me to be able to integrate it, because I could separate it into two things that were being subtracted from one another, whereas I couldn't separate this into that, two things that were being added or subtracted. All right, that's probably a good place to stop. Let me check where we're at here. We are at problem 25 on page 502. Yeah, this is a good way to go using this test, because what happens is that I'll come across subtle points of calculus that I can talk about even though we're not looking at a problem on the test like that.
Right.
So, all right. Diana, we'll talk to you next time.
All right. Thank you.